Use our CVPR work rethinking of objectives of Vector-Quantized tokenizer for image synthesis. Let's first cover the background of VQ-based generative models. It contains two training stages. The first, train a VQ image tokenizer to compress image into discrete sequence, and this phase is referred to reconstruction. The second stage is train a generative transformer to learn underlying distribution in the discrete latent space, and the sampling from generative transformer is referred to generation. We can see some design of generative transformer like autoregressive transformer in VRT-VQ GAN, not autoregressive transformer in master gate, and the discrete diffusion in VQ diffusion. So we can find the VQ image tokenizer is a foundation component in VQ-based generative models. So how to design a good VQ image tokenizer? We can cover some typical design of VQ tokenizers. The first is VRT-VQ GAN. It uses small conversion ratio, small code dimension, but large codable size, which result in a better reconstruction fidelity. And the residual quantization recursively quantized with a shared codebook to precisely approximate the feature map and achieve a better reconstruction FID. And the more VQ use multi-channel quantization with a shared codebook and the modulation enhanced encoder to achieve the best fidelity, reconstruction fidelity. But how the improved reconstruction of VQ tokenizer affect the generation? In our paper, we want to investigate this problem. We summarize why previous VQ tokenizer lack such investigation because one is their underlying assumption that's better reconstruction by the generation, and they lack a visualization pipeline to compare the generation result of various VQ tokenizer. Previous visualization usually compare two random sets of image, but we are curious about how transformer model a specific image. So the key idea is to reduce the flexibility of sampling process by providing ground truth context of reference image. When provide a reference image, we first get its ground truth token by VQ image tokenizer encoder, and we use a trained autoregressive transformer to predict next token by provide the ground truth context token, and compare these two results. From our visualization and some toy experiment, we find better reconstruction fidelity sometimes make worse generation. It's because the generation and the reconstruction have a large gap when we visualize their results. So model level details in tokenizer may not benefit generation. What if we reduce the details by enriching semantic in tokenizer? In order to control the detail and semantic balance, we introduce a reversed version of perceptual loss. And we can see when the semantic ratio is increased, the generation performance keeps improving. And when increase the semantic ratio in VQ tokenizer, the generative transformer better model the texture and the structures. So our observation revealed the two competing objectives in optimizing VQ tokenizer, that's details preservation and semantic compression. Previous work mainly focused on improving the details preservation, but how to balance these two objectives, we introduced a semantic quantized GAN to tackle this problem. The semantic quantized GAN have two-phase chaining. The first is use the semantic enhanced perceptual loss, which pursue the objective of semantic compression. And then in second phase, we fix the encoder and the codebook, only fine-tune the decoder with low-level perceptual loss. Since the transformer training only requires the encoder and the codebook, so the transformer training is fixed, and the refined local details will not influence the transformer training. We can see our decoder only fine-tuning improves the local details but not influence the transformer training. From the quantitative reconstruction results, we can see our reconstruction is not surpass the previous VQ tokenizer, but in generation, our results remarkable improve the previous VQ-based generative models by a large generation FID. Here's the generation results of our methods. So the take-home conclusion of our work is the relation between the reconstruction fidelity of VQ tokenizer and the generation performance is complex, which should be noticed and deeply investigated in designing VQ tokenizer.